Venturing further beyond the orbit of Jupiter, we arrive at Saturn, arguably one of the most photogenic planets in our solar system. Its iconic rings, made of ice and rock, are visible even through small telescopes on Earth, but Hubble has taken that view to a whole new level. The telescope has allowed us to observe seasonal changes in the rings and has detected mysterious wave patterns caused by gravitational interactions with Saturn's many moons. Saturn's largest moon, Titan, is another jewel in its system. Hubble's ultraviolet and infrared capabilities have helped scientists peer through its thick, hazy atmosphere. What lies beneath is a world that bears eerie similarities to early Earth, with lakes of liquid methane, weather systems, and possibly even cryovolcanoes that spew icy slush instead of molten lava. Titan is one of the most promising locations for studying prebiotic chemistry and the potential for alien life. From Saturn, our journey continues outward to Uranus and Neptune, the ice giants. These planets are harder to study due to their distance and faintness, but Hubble has offered us rare glimpses of their atmospheres. Uranus, with its extreme axial tilt, experiences seasons that last over 20 years. Hubble has observed the formation and dissipation of bright storm systems as the planet transitions from one season to another. Neptune, the furthest known major planet from the Sun, is a dynamic world of violent storms and high-speed winds. One of the most fascinating features ever captured by Hubble was the appearance and sudden disappearance of dark storms on Neptune's surface, phenomena that remain mysterious to scientists to this day. These transient storms rival the Great Red Spot in size and drama, yet they come and go within years. Beyond Neptune lies the Kuiper Belt, a vast region populated by icy bodies and dwarf planets like Pluto, Haumea, and Makemake. While Pluto was once considered the 9th planet, it now holds its place as one of the most studied dwarf planets, thanks in part to observations made by Hubble. The telescope helped discover Pluto's smaller moons and captured detailed maps of its surface long before the New Horizons mission arrived. In fact, Hubble played a pivotal role in selecting the post-Pluto target for New Horizons, the object known as Arrokoth, previously Ultima Thule. Its unusual shape, 2 lobes joined together like a snowman, was first observed by Hubble, prompting mission scientists to consider it a prime target. Later, when New Horizons flew by, it confirmed what Hubble had seen from billions of miles away. The ability of Hubble to spot and analyze such distant, dim objects in the Kuiper Belt is a testament to its power and sensitivity. In doing so, it has expanded our understanding of the solar system's formation and the kinds of bodies that exist on its fringes. And even farther still, past the Kuiper Belt, lies the hypothetical Oort cloud, a shell of icy objects that may encase the entire solar system. While Hubble hasn't directly observed the Oort cloud, its studies of comet trajectories and outer solar system dynamics have helped scientists infer its existence. As we explore further, we begin to realize how vast, dynamic, and intricate our solar system truly is. It's not just a collection of planets orbiting the Sun. It's a diverse, ever-changing ecosystem of worlds, each with its own mysteries and marvels. This insight highlights the continuous discoveries enabled by Hubble, enriching our understanding of the cosmos. As we look ahead into the future of space exploration, it's natural to wonder, what comes after Hubble? The answer isn't the end of a journey, but rather the start of a new chapter built on everything Hubble has given us. The James Webb Space Telescope, JWST, often described as Hubble's successor, has already begun capturing the public's imagination with its incredible infrared capabilities. While JWST peers further into the universe's origins, Hubble continues to monitor the solar system and nearby galaxies, creating a multi-generational synergy. Together, they give us a deeper, richer, more detailed picture of space than ever before. And then there's the Nancy Grace Roman Space Telescope, slated for launch in the coming years. This wide-field infrared telescope will capture vast portions of the sky at once, further enhancing what Hubble started. Its goal is not just discovery, but understanding, mapping dark matter, measuring the expansion of the universe, and finding thousands of new exoplanets. But even as new telescopes rise, Hubble remains irreplaceable. Its unique position, spectral capabilities, and decades-long archive give it unmatched value. It acts as a bridge between Earth and the cosmos, between past and future missions, between scientific theory and visual proof. Hubble's endurance also symbolizes human perseverance. Through budget challenges, mechanical failures, and the passing of generations of scientists, the telescope has endured. It has grown not just as a machine, but as a beacon of what humanity can achieve when we reach upward together. The telescope has also taught us to be humble. For every question it answered, Hubble raised dozens more. It showed us strange moons, unexpected atmospheres, disappearing storms, and alien visitors from other star systems. In doing so, it reminded us that knowledge is never finished. It's always unfolding. More importantly, Hubble changed the narrative of exploration. No longer are space missions simply about planting flags or collecting samples. They are about storytelling, about understanding the forces, patterns, and mysteries that shape our universe and ourselves. As a new generation of scientists, engineers, students, and dreamers look to the stars, Hubble will remain part of their foundation. It has set the standard for excellence, discovery, and inspiration. Its images are not just data, they are windows into the infinite. And while one day Hubble may finally power down, its spirit will live on, not just in observatories and missions, but in every curious mind it ever touched. That may be its greatest legacy of all. This insight highlights the continuous discoveries enabled by Hubble, enriching our understanding of the cosmos. While the images Hubble captures are visually breathtaking, what lies beneath is even more powerful: data. Every pixel, every spectrum, every observation made by Hubble is packed with information. It's this data that drives scientific discovery, often long after the initial image has been taken. When Hubble takes a snapshot of a planet or a comet, it's not just for visual effect. Scientists can analyze the light being reflected or emitted from the object to determine its composition, motion, temperature, and more. This process, called spectroscopy, allows researchers to decode the chemical fingerprints of celestial bodies. Take Mars, for example. Hubble has analyzed its atmosphere to track seasonal dust storms and measure water vapor in the thin Martian air. Even subtle variations help scientists model the planet's climate and assess its potential to support life, now or in the past. Or consider Saturn's rings. Hubble has used reflected light to determine the composition of the ice particles within the rings, revealing the age, density, and evolutionary history of the structures. These aren't just decorative features, they're records of past collisions, gravitational interactions, and planetary change. Data from Hubble is also helping scientists understand the concept of migration within the solar system. By studying the orbits and compositions of Kuiper Belt objects and comparing them to inner solar system bodies, researchers can piece together how the solar system's architecture may have shifted over billions of years. In many cases, it's not a single image that unlocks a mystery, but a sequence over time. Hubble's longevity has made it uniquely valuable in this regard. Some objects have been revisited dozens of times, each pass adding new layers of detail and forming a timeline of cosmic evolution. This is particularly important in the study of variable phenomena, storms on Jupiter, plume activity on Europa, and changes in asteroid brightness due to rotation or collisions. These time-lapse datasets allow for dynamic models, not just static snapshots, of how these objects behave. The power of Hubble's data has also been magnified by global collaboration. All of its data is archived and accessible to scientists around the world. This open science model means that a photo taken years ago might inspire a new study today, based on questions we didn't even know to ask at the time. Moreover, Hubble's role in education and inspiration cannot be overstated. Teachers, students, and citizen scientists have used Hubble images and datasets for everything from science fair projects to advanced astrophysics research. Its legacy includes not just discoveries, but future discoverers. The ability to turn photons into insight, to convert distant starlight into answers about our origins, is what makes Hubble not just a telescope, but a storyteller. It doesn't just show us the universe. It helps us understand what it means. This insight highlights the continuous discoveries enabled by Hubble, enriching our understanding of the cosmos. As we continue our exploration of the solar system through Hubble's lens, it becomes clear that the telescope's contributions are not limited to the study of planets alone. Hubble has also focused its gaze on comets, asteroids, and other small solar system bodies, often capturing them at moments of extraordinary activity. One of the most iconic events captured by Hubble was the collision of comet Shoemaker-Levy 9 with Jupiter in 1994. The telescope provided dramatic images of the aftermath, dark scars stretching across the gas giant's atmosphere, each larger than Earth itself. These images offered scientists a rare look into planetary impacts and their consequences, reinforcing the dynamic and occasionally violent nature of our solar system. Since then, Hubble has continued monitoring comets as they plunge toward the Sun or travel along their elliptical paths. It has observed comet disintegrations, such as Comet Ison in 2013, and even discovered new comets hurtling in from the outer solar system. These observations help us understand the composition of the early solar system, as many of these icy travelers are pristine remnants from that time. Asteroids, too, have come under Hubble's scrutiny. One fascinating discovery was the asteroid P2013 R3, which was seen breaking apart into multiple smaller pieces. This level of detail, captured from over 300 million miles away, gives scientists insight into the fragile structure and behavior of these small bodies, which may someday become resources or hazards for future space missions. Even more remarkably, Hubble has observed objects with bizarre orbits and strange behaviors. For instance, it spotted an asteroid with 6 comet-like tails, designated Oumuamua pan-stars, defying classification and sparking debates about the boundaries between asteroids and comets. These observations go beyond curiosity. They inform our planetary defense initiatives, helping scientists model the trajectories of near-Earth objects, NEOs, and assess impact probabilities. Hubble's precision makes it a key player in these global efforts to protect our planet from potential collisions. Another critical target of Hubble's attention has been moons, especially those orbiting the outer planets. Beyond Europa, it has studied Enceladus, a moon of Saturn with geysers erupting from its surface, and Ganymede, the largest moon in the solar system, which may also harbor a subsurface ocean. Each of these discoveries is a step closer to answering one of humanity's greatest questions. Are we alone? The synergy between Hubble and other space missions cannot be overstated. While orbiters and landers provide close-up, high-resolution data, Hubble's wide-angle, multi-wavelength perspective offers context and helps select targets for future exploration. In many ways, Hubble is the scout that guides deeper missions. As we trace the journey from comets to moons and from asteroids to dwarf planets, Hubble acts as a lens, not just on our solar system, but on our cosmic heritage. It teaches us that even the smallest bodies hold secrets essential to understanding the grand story of our origins. This insight highlights the continuous discoveries enabled by Hubble, enriching our understanding of the cosmos. Hubble has now been in space for over 33 years, and its mission has been a resounding success. It was never originally designed to observe objects within our own solar system, but that hasn't stopped it from doing exactly that over the course of its operation. In fact, Hubble has provided us with some of the most memorable and scientifically valuable glimpses into our celestial neighborhood, images and data that we would have otherwise missed. Not every planet or object in our solar system has its own dedicated mission. Launching probes to each celestial body is costly, complex, and takes years of planning and execution. But Hubble, with its location outside Earth's atmosphere and its broad field of view, has been able to step in and offer a kind of universal observatory. It has filled in many of the gaps and brought to light things we didn't know we were missing. So let's take a journey, a visual odyssey, through our solar system, from Earth all the way to its outermost edges. We'll explore planets, moons, dwarf planets, and mysterious objects floating in the Kuiper Belt, all through the eyes of this incredible space telescope. From its perch in low Earth orbit, Hubble has captured our home planet in brilliant clarity, but its real magic lies in what it sees beyond Earth. As we move outward, we start with the Moon. Though it's just 250,000 miles away, Hubble's images of the lunar surface show intricate crater patterns, mineral distributions, and geological histories if the Moon were just next door. Moving past the Moon, we approach Mars, the red planet. While orbiters and landers like Perseverance provide up-close data, Hubble offers a unique wide-angle perspective. Its observations of dust storms, polar ice caps, and seasonal changes help us understand Mars as a living, evolving world. Next is Jupiter, a gas giant so massive that it could contain all the other planets in the solar system combined. Hubble's view of Jupiter is breathtaking. Its great red spot, a centuries-old storm, shifts, morphs, and shrinks over time. Hubble helps scientists study this and other atmospheric phenomena, including the beautiful auroras at Jupiter's poles. Hubble has also been instrumental in studying Jupiter's moons, especially Europa. Covered in ice, Europa is believed to harbor a subsurface ocean, possibly capable of supporting life. Hubble detected water vapor plumes erupting from its surface, evidence that this moon may be more active than we previously thought. And this is only the beginning. From Saturn's rings to Uranus's strange tilt and Neptune's dark storms, Hubble has painted an intricate portrait of our entire solar system. This insight highlights the continuous discoveries enabled by Hubble, enriching our understanding of the cosmos. One of Hubble's most powerful contributions is not in capturing a single moment, but in revealing how celestial bodies change over time. With over 3 decades of continuous service, Hubble has amassed a long-term data set unlike any other. This continuity allows scientists to monitor the evolution of planets, moons, and comets with unprecedented clarity. Let's take Jupiter again as an example. Hubble has documented changes in the Great Red Spot, once massive and dominating the planet's southern hemisphere. Over the years, the storm has been steadily shrinking. Its color and intensity have also varied. This isn't just a curiosity. It's an atmospheric phenomenon with direct ties to the planet's internal dynamics and energy balance. Saturn's rings are another dynamic system under Hubble's watchful eye. Although they appear permanent, the rings are constantly evolving. Hubble has detected clumps, gaps, and waves forming and dissolving over time. One of the most fascinating findings is the possibility that the rings are slowly disappearing, a process that may take only a few 100 million years. Uranus and Neptune, the ice giants, also reveal long-term changes through Hubble's lens. On Uranus, storm systems have been spotted forming as seasons change. The planet's extreme tilt causes dramatic seasonal variation, and Hubble helps chart how those changes play out in real time. On Neptune, dark spots, massive storm systems, appear and vanish within years. Thanks to Hubble, we have been able to observe the full life cycle of one such storm, including its unexpected reversal in direction. These long-term observations are vital for building accurate climate models, not just for distant planets, but as analogs for Earth. Understanding how large-scale storms form, evolve, and dissipate helps scientists refine their understanding of weather and climate mechanics across planetary environments. Comets, too, benefit from this type of persistent tracking. Hubble has captured comets as they approach the Sun, break apart, or develop unexpected jets and tails. By comparing observations taken over days, months, or even decades, scientists can understand what triggers these changes, what lies beneath the icy surface, and how these ancient bodies behave in solar heat. Even the Sun's influence can be studied indirectly. Hubble monitors how solar activity, such as flares and wind, affects planetary auroras, atmospheric stripping, and surface radiation. These interactions shape the conditions on planets and moons and are key to assessing habitability. And beyond simple observation, Hubble's data has allowed for predictive modeling. In some cases, Hubble has detected changes that later missions confirmed in more detail. By spotting trends, scientists can anticipate when to focus other instruments or prepare for significant events, like the next great storm on Saturn or an incoming interstellar object. This is how Hubble becomes more than a camera. It's a clock, a diary, and a window into the living processes of our solar system. With each passing year, its long memory becomes more valuable, creating a narrative of transformation and persistence among the stars. This insight highlights the continuous discoveries enabled by Hubble, enriching our understanding of the cosmos. Beyond the orbit of Neptune lies one of the most mysterious and least explored regions of our solar system, the Kuiper Belt. This vast icy realm is home to thousands of frozen objects, including dwarf planets, comets, and remnants from the earliest days of our solar system. And while it's incredibly distant, Hubble has brought this remote frontier into sharp focus. Thanks to Hubble's powerful optics, scientists have been able to detect, track, and characterize dozens of Kuiper Belt objects, KBOs. These include well-known bodies like Pluto and Eris, but also many smaller, irregularly shaped objects that had previously gone unnoticed. With Hubble's help, we've learned that these objects are incredibly diverse in size, shape, color, and composition. Hubble's role in exploring the Kuiper Belt became even more prominent during the New Horizons mission. After its historic flyby of Pluto, the spacecraft needed a new target to explore. Hubble was tasked with searching the outer solar system to find suitable candidates. It succeeded in identifying 2014 MU-69, later named Arrokoth, as the perfect follow-up. Arrokoth turned out to be one of the most intriguing objects ever studied. Hubble had first observed it as a faint point of light, but from that alone, it helped plot New Horizons' course. When the spacecraft finally reached Arrokoth, it revealed a contact binary, two lobes gently pressed together like a snowman, untouched for billions of years. Hubble had seen it first, proving that even the faintest smudges of light can hold priceless secrets. Beyond Arrokoth, Hubble has helped identify binary KBOs, pairs of objects orbiting each other in delicate cosmic dances. These discoveries challenge and refine models of how planets and small bodies form. Do they collide and fuse, or do they slowly spiral into gravitational embraces? Hubble's data helps scientists test these ideas against reality. One surprising result of Hubble's surveys is how alive the Kuiper Belt appears. While these objects seem inert, they can have thin atmospheres, outgassing behavior, or surface changes due to distant solar heating. Some KBOs show colors that suggest complex organics, possible precursors to life's ingredients. This region also serves as a cosmic time capsule. Because Kuiper Belt objects are so far from the Sun, they've been preserved in near-pristine condition. Studying them is like reading pages from the solar system's origin story, pages that have remained untouched for 4.6 billion years. Moreover, Hubble's ability to study these dim and distant bodies lays groundwork for future missions. Scientists are already planning next-generation spacecraft to orbit or even land on KBOs. But without Hubble's reconnaissance, such missions would be flying blind. The Kuiper Belt also leads us to the even more mysterious Oort cloud, a hypothetical shell of icy bodies that could extend halfway to the next star. While Hubble can't see the Oort cloud directly, its observations of long-period comets and distant solar system dynamics help confirm its existence. In this icy wilderness, Hubble acts as both scout and storyteller. It takes the invisible and makes it real, guiding our curiosity into territories once deemed unreachable. This insight highlights the continuous discoveries enabled by Hubble, enriching our understanding of the cosmos. In recent years, a new and unexpected class of celestial objects has captured the attention of astronomers worldwide: interstellar visitors. These are objects that did not originate within our solar system, but are merely passing through. And once again, Hubble has played a vital role in documenting and analyzing these rare encounters. The first confirmed interstellar object was discovered in 2017 and named Oumuamua. Unlike anything previously observed, it had an elongated cigar-like shape and no visible tail like a typical comet. While ground-based observatories first spotted it, Hubble was essential in tracking its trajectory and velocity with extreme precision, confirming that it was not gravitationally bound to the Sun. Though Oumuamua exited our solar system too quickly to reveal all its secrets, it raised fascinating questions. How common are such interstellar objects? What are they made of? Do they carry materials or even organic molecules from distant star systems? In 2019, another interstellar traveler appeared, Comet 2I Borisov. This time, Hubble was ready. With its sensitive optics and spectral instruments, Hubble captured detailed images and data that showed Borisov was more similar to comets in our own solar system, but with key differences in its chemical makeup. It provided the first direct evidence that other planetary systems form comets and eject them into space just like ours does. Hubble's observations of Borisov revealed a composition richer in carbon monoxide than most local comets. This suggests that it formed in an environment much colder than our solar system's outskirts, perhaps in a distant icy realm around another star. Such insights are invaluable, giving us our first sample of the building blocks from another star system without leaving home. What's astonishing is that these fleeting objects, traveling at tens of kilometers per second, can be caught and analyzed from billions of kilometers away. Hubble's ability to lock on and study them in such detail reflects the precision and flexibility of its instruments. Moreover, these observations contribute to planetary defense strategies. Understanding the paths and behaviors of non-native objects helps calibrate detection systems and prediction models. As we expect more interstellar visitors in the future, telescopes like Hubble remain on standby to capture their brief but informative appearances. Some scientists speculate that interstellar objects might even carry clues to the origin of life. If organic molecules are discovered in such visitors, it could support the theory of panspermia, the idea that life can spread from one planetary system to another via comets or meteorites. By expanding our perspective beyond the solar system, these encounters show that our neighborhood is not isolated. The cosmos is active, dynamic, and interconnected. Hubble helps bridge the gap between the familiar and the foreign, between home and the stars. This insight highlights the continuous discoveries enabled by Hubble, enriching our understanding of the cosmos. One of Hubble's most remarkable capabilities is its ability to see the universe in wavelengths of light invisible to the human eye. While we perceive only the narrow band of visible light, Hubble can observe ultraviolet and near-infrared light, allowing it to reveal secrets that would otherwise remain hidden. When it comes to studying solar system objects, this feature is a game-changer. For instance, ultraviolet imaging can highlight auroras on planets like Jupiter and Saturn, giving scientists real-time information about how solar wind interacts with their magnetic fields. These glowing light shows are not only visually stunning, but also key indicators of planetary atmospheres and space weather conditions. Infrared imaging, on the other hand, lets Hubble penetrate the thick, obscuring clouds of planetary atmospheres. It has revealed detailed weather patterns on the gas giants and helped uncover surface features on moons shrouded in haze. Through this lens, Hubble has observed heat signatures that hint at subsurface oceans, cryovolcanism, or unexpected geological activity. Beyond planets, these extended wavelengths have been essential in studying dust within the solar system. Dust rings around planets, tails of comets, and even the thin, faint debris disks surrounding some asteroids are only visible with Hubble's advanced optics. The ability to image these structures helps piece together the dynamism and history of collisions and formations within our solar neighborhood. Perhaps most astonishing is how Hubble's multi-wavelength vision bridges planetary science and astronomy. When scientists observe a comet emitting strange light patterns or track faint, dim trans-Neptunian objects in the Kuiper Belt, they rely on Hubble's spectral versatility to analyze their composition. What molecules are present, what processes are occurring, and how these objects relate to the early solar system. For example, in 2020, Hubble observed a rare interstellar visitor, comet 2I Borisov, as it passed through our solar system. By studying its ultraviolet spectrum, Hubble confirmed that this object was fundamentally different from any comet native to our own system. It provided compelling evidence that other planetary systems form comets similarly to ours, but with unique variations. These invisible wavelengths also contribute to the detection of changes over time. Scientists often return to the same object year after year with Hubble to track seasonal changes, storm evolution, or shifting features. With each pass, a new layer is revealed, deepening our understanding of the living, breathing nature of planets and moons. What's more, this invisible light is the gateway to discovering the building blocks of life. By identifying organic molecules, water signatures, and the fingerprints of complex chemistry on distant moons or icy objects, Hubble helps expand the possibilities of where life might exist in our cosmic backyard. Ultimately, Hubble's ability to see what we cannot gives humanity a superpower, vision beyond biology. It reminds us that the universe is far richer than our senses allow, and that science can extend our reach into dimensions we were never meant to perceive. This insight highlights the continuous discoveries enabled by Hubble, enriching our understanding of the cosmos. Although Hubble is a marvel in its own right, its true strength often shines when it works in tandem with other spacecraft. Collaboration between missions creates a synergy where the sum is far greater than its parts. In the modern age of space science, this cooperation is what unlocks the deepest cosmic mysteries. A perfect example of this teamwork is the New Horizons mission. Before New Horizons approached Pluto in 2015, Hubble played a crucial role by mapping Pluto's surface and identifying small moons orbiting it, information that guided the trajectory and expectations of the flyby. Later, when New Horizons headed toward the Kuiper Belt object Arrokoth, it was Hubble that discovered and characterized the target, making the extended mission possible. Similarly, Hubble has supported missions like Juno at Jupiter and Cassini at Saturn by providing broad-scale context to complement the up-close views from orbiters. While Juno measures magnetic fields and interior structures, Hubble watches from afar, monitoring changes in Jupiter's atmosphere and auroras to offer a global picture of the planet's behavior. This synergy extends to Earth-orbiting telescopes and ground-based observatories. For instance, when the James Webb Space Telescope launched, many wondered if Hubble would become obsolete. In truth, the two telescopes are designed to complement one another. Where Webb specializes in deep infrared observations, Hubble remains unmatched in ultraviolet and visible light. Working together, they can observe the same targets across multiple wavelengths, providing a holistic view of planetary phenomena. During the study of exoplanet atmospheres, Hubble has pioneered techniques that Webb now extends. By measuring the dimming of starlight as a planet passes in front of its host star, Hubble can detect atmospheric components like hydrogen, water vapor, and even potential biosignatures. These same techniques are now being scaled up and refined by Webb for more distant and smaller planets. In the case of solar system monitoring, Hubble often acts as the scout, identifying targets worthy of deeper investigation. When a new comet is detected, or a sudden change in a planet's atmosphere occurs, Hubble is often called upon to capture detailed images immediately. These observations can then prompt closer inspections by other telescopes, or even the planning of future missions. Moreover, Hubble's influence reaches back decades and forward into the future. Its data has helped define mission parameters for proposed robotic explorers and landers. By characterizing surface compositions and environmental conditions on moons like Europa or Enceladus, Hubble has laid the groundwork for future astrobiological missions. It's important to recognize that space exploration is not a solo endeavor. It's a relay race across generations of instruments and missions, each handing the baton to the next. Hubble's role in this race is indispensable. It doesn't just observe, it guides, connects, and amplifies the efforts of others. Through these collaborations, Hubble reinforces a fundamental truth of science, that progress is built not in isolation, but in partnership. And in that partnership, we find the path to discovery. This insight highlights the continuous discoveries enabled by Hubble, enriching our understanding of the cosmos.